Now let's take a look at it. How is it possible that the Organica plants are using much less energy? In order to understand that, we have to go deep into the reactor, and we have to take a look at the biomass that develops on the root and on the biofilm. Remember, we have established that there are 4 times as many species and also 4 times the volume of the biomass. But how is that possible, and what does it look like? Let's take a look at these pictures. What you see on the left-hand side is a typical biofilm that grows on the plant root. And for comparison reasons, you see a typical MBBR carrier with the corresponding biofilm that grows on that. What you see on the right-hand side, MBBR, stands for moving bed bioreactor. And in those technologies, what you have is these little tiny, about 1 centimeter diameter little plastic carriers that are put into the water to allow organisms to grow on that. The reason I'm showing these 2 slides, and what you see is on the top, is the right scale comparison. To see the comparison of the biofilm that grows on the plant root or the biomodule compared to the plastic carrier that you would find in a traditional MBBR plant. And in order to compare, let's take a look at the next picture, where on the left-hand side, you see the structure in a graphical representation of the biofilm that grows in an Organica system. And on the right-hand side, you see the biofilm that would grow on an MBBR carrier. There are very important differences. For one, as you can see, the one on the left-hand side is considerably more thicker. It's like 2 orders of magnitude deeper. But it's also, what you can see is that the structure is very loose. It's like seaweed. It's very fluffy. And that, on the left-hand side, in an Organica plant, that fluffy structure allows for a much better mass transfer characteristics. So both for the food can be much better absorbed in a much more efficient way, as well as the necessary oxygen for all these organisms that form or compose this biofilm. On the next slide, on the left-hand side, you can see a typical biomodule. Maybe you can make out the construction worker on the lower left-hand corner. And on the right-hand side, you see the biofilm that grows on this media. And again, it's important to note that you have a lot of this biomass. Remember, it's more than 12 kilos per cubic meter. But also you can see it's very fluffy. And there's a third element that is important to notice here, that as we look at this picture, we can see that the water is relatively clear. So keep in mind that we're keeping all this biomass in the reactor, but all of the biomass is attached. Very little of the creatures, very few of them, are swimming. That means that the suspended matter in the water is very low. This is why it's relatively clear. Now, why is this important? It's very important because it directly impacts how efficiently you can run a treatment plant. What you see on the next slide is a schematic. What happens? How does the oxygen get actually into the water? The organisms that use the oxygen need it in a dissolved matter. So we have the fine bubble aeration in every traditional treatment plant as well as in an Organica plant. And these tiny little bubbles are traveling from the bottom of the reactor all the way up to the top, 5-6 meters. And during this travel, these are really, really tiny bubbles. And during this travel is that the air from the bubble and the oxygen that's inside the bubble dissolves, makes its way, diffuses into the water around it. Now, in clean water, this diffusion, this transfer of oxygen between the bubble and the water is uninhibited. And actually, by definition, the efficiency of the transfer is considered 1 for clean water. Now, the moment you start to have particles in the water, those particles interfere on the surface of these little bubbles with that transfer. So the more little particle attaches to the bubble, the less ability for the oxygen to transfer into the water. So that means the oxygen transfer efficiency, actually that coefficient, which is called the oxygen transfer coefficient, is less and less the more and more particles you have in the water. So in the next slide, what you see is a graph. On the vertical axis, you see what is called the oxygen, the alpha, which is the oxygen transfer efficiency. And on the horizontal axis, you see how much particles are in the water, which is TSS really, which is for total suspended solids. Now, in a traditional, let's say an MBR, which stands for membrane bioreactor, which is run by, let's say, 12 kilograms of biomass in the water, that oxygen transfer efficiency may be as low as 0.5 or even lower, because you have that many particles in the water in suspension. In a traditional activity sludge plant, which is, let's say, is being run at 4,000 mLSS, that alpha, the oxygen transfer efficiency, will be around 0.55, because that's if you have like 4,000 milligrams of material in suspension. Now, in an Organica plant, because all the biomass, you have a lot of biomass, but all of it is attached, very little is swimming in the water. That means that you can keep the oxygen transfer efficiency above 0.9. And the difference between the two, in other words, between the 0.9 and 0.55 or 0.5 or even lower numbers, is clear energy savings. So the lower energy use has a very simple physical explanation. It can be traced back to the higher oxygen transfer efficiency. The largest cost component in running a wastewater treatment plant is actually energy use. So that's why the lower energy, 30, 40, sometimes 50% lower energy use actually translates to that much lower operational expenses. So we can establish that Organica treatment plants cost less to operate.